Good morning, ma'am. Ma'am, are we audible?
Yes. Yes. Good morning.
Yes, audible.
Yes, ma'am. We will start sharply at 10:30, ma'am. Madam, shall we start? Ma'am?
Yes, I am ready.
Yes, ma'am. Yes, thank you. So we welcome you all to this fourth day FDP on additive manufacturing process and application. At this moment, we are happy to inform you that we have more participants from international many countries. So all this possible only because of the eminent speakers like you. Now I'm very happy and willing to wholeheartedly welcome ma'am. She has held Indrani Sen, Associate Professor, Department of Metallurgy and Materials Engineering, IIT Kharagpur. She has held various professional positions as visiting scientist at Oak Ridge National Lab, USA. She has been on research stay to Alexander von Humboldt renowned research stay at Ruhr University, Bochum, Germany. She has done a postdoctoral research at the University of Technology, Germany. She is a reviewer in many leading journals. She has published more than 31 international journals and book chapters in referred international level journals. Her research area includes shape memory alloys and smart materials, structural materials, additive and laser-based manufacturing, marine structural engineering. She has many noticeable awards and recognitions from AICTE, MHRD, Humboldt Foundation, Germany, Transactions of Indian Institute of Metals, IISc, and IIT. She has also received Venus International Women Award for being Outstanding Women in Engineering, VIVA 2018. She worked as a principal investigator and co-principal investigator in many sponsored research projects. So we welcome you, ma'am, to share the session. Thank you.
Thank you very much for a very nice introduction. And I'm happy to be here today to connect with all of you, to deliver my lecture on a very state-of-the-art topic on additive manufacturing. Before I start, I'd just like to have an idea of the background of all the participants here. Like, are you from the mechanical engineering background or maybe metallurgy or something else? It will help me structure the presentation in a way that everyone can connect to.
Ma'am, automobile engineering, ma'am. Krishna Kumar from
Yeah. Okay, very nice.
So, Madam Poolagan from Mechanical Engineering, Madam. Yeah.
Thank you.
Yeah.
Okay, so I assume that most of you are from mechanical, automobile, someone said, so mostly like that, right? Are there anyone from materials or metallurgy? Anything related?
Yes, ma'am. Yes, ma'am.
Okay, good.
In powder metallurgy, I am pursuing PhD.
Okay, okay, very good. Okay, fine. So that means that we have a mixed audience from a different background. Fine. So let me just share my screen to show what I have in store. And the full screen is visible?
Yes, ma'am, your screen is visible.
In the full screen mode, right?
Yes, full screen, yeah.
Okay, thank you very much. So now I will turn off my video and let's focus on the topic.
Okay.
Okay, so as I said, I'm very much happy to be here. And this is very nicely organized by this college. I understand that this is named as SMVEC. That's how you prefer to name it. So we are going to understand something about how the microstructures of the additively manufactured materials changes and how does that affect the mechanical property. I'm sure you have heard to many of the interesting lectures so far where the details of additive manufacturing has been emphasized, and we are trying to look into a little more different perspective on the evolution of microstructure there. So before I start, let me just give you a brief of where I come from and what do I do. So this is the most of the major institutes of India, and I come right from here. Okay, so this is the oldest IIT of this IIT system, established almost 70 years back in 1951, and we just had our 71st foundation day last week on 18th. So this is our main building, very marvelous building here. And actually, this main building is a replica of the old building that we had. So when the IIT has first started in 1951, right after the independence, this was the building which was found, and the entire campus is actually placed on the area of Hijli detention camp. So that is the place where we still have a jail where the freedom fighters used to be kept. And this is a very sanctioned place where the IIT has been built by the then Prime Minister Pandit Jawaharlal Nehru. So we are very fortunate to work here, and this is my group. A year before the lockdown started, some of them has graduated and left the group, and new members have joined. But we are still under partial lockdown. So yeah. And this is my overall broad area of work. So I mostly my group is focused on studying the microstructure property correlations of materials. Now, different category of materials, from conventionally processed materials to additively manufactured materials, and we looked at the properties at different scale. The macro scale, the typical fracture fatigue behaviors are being studied extensively in details, as well as in the micro and nano levels also, where we do nano indentation and micropillar compression and something like that. Apart from that, we are also developing our expertise on in vitro mechanical behavior. So this is very much important for materials which are used for biomedical application. We want to figure out that how the properties of the materials will be when these are placed inside the human body. Okay, in similar kind of environment where we have the body fluids and the body temperature, how the performance of the material, like the fracture and fatigue behavior of the materials will be. We are also determined to find out the high temperature behavior of materials. Those are used for aerospace application at very high temperature of 700, 800 degrees centigrade. How does the materials fracture or the fatigue behavior of the material? So these are something of our interest too. And we work on a variety of materials such as different kinds of steel, of course, and then comes the nickel titanium, which is a shape memory alloy, a smart alloy, and titanium based materials, super alloys, and so on. So these are my contact information. If anybody is interested to contact with me in future, also can do so. I'll be happy to answer your questions. Okay, so now moving to the topic. So before we start on additive manufacturing, let's focus on what we had, what we used, what were in practice for several decades. For the metallic systems, particularly for the metallic system. So whenever we have something to make out of the metallic system, we use the following kind of procedures: casting, and then different kinds of machining operations. Okay, these are some of the pictures of casting and different varieties of machining. The schematics are shown here, and these are very well explained in a video which I'm going to show you, where the different processes, the different machining processes are being shown very briefly. Also, when I start the video, please confirm me if it is audible.
Video is audible, ma'am.
It is audible. Okay,
Yes,
thank you.
In straight turning, the tool is fed parallel to the axis of the work to reduce its diameter so that the final diameter is the same at each end. Removing a significant amount of material in one pass is called rough turning. The final lighter cut that creates a smooth surface finish is called finish turning. Taper turning produces a taper along the axis of the workpiece. Tapers are produced by offsetting the tailstock from centerline or by using a taper attachment. Short, steep tapers can be turned using a compound rest. Contour turning or profiling was formerly performed by having the single-point cutting tool trace a template of the desired profile shape. This has largely been replaced by CNC turning, in which the desired contour is simply programmed into the machine, which directs a cutting tool to cut the contour. Forming is another alternative for generating complicated shapes. The tool having the desired form or geometry is advanced perpendicular to the axis of rotation, reproducing the tool shape in the workpiece. Forming is commonly performed on automatic screw machines. Chamfering eliminates sharp corners from a workpiece and is a good safety measure. Typically, chamfering breaks corners at a 45-degree angle. Grooving creates a groove or recess using a tool that is usually the size and shape of the required groove. Some grooving tools can also widen a groove by traversing side to side after plunging into the workpiece.
Okay, so this is mostly what we do for machining. So any kind of shape, whatever it is, a simple or a complex one, we have to pursue different kind of machining operations to give that particular shape. And if you have noted in that video that when we are doing such kind of machining operations, there are these chips coming out, right? So this kind of chips are always coming out while we are doing the machining, and these are coming out actually quite extensively. So when those kind of machining operations are inevitable, this also comes with some drawbacks. For example, the tool that we are used for machining gets weared, and this chip formation, which are undesirable, that even varies the properties of the surface, properties of the materials as well. So there is a huge amount of material that are being wasted simply because of this machining operations, which could not be used any further. And apart from machining, we also do, even on the machine samples also, we sometimes need to do grinding and polishing to get a final appearance. Okay, so based on this, just summarized the manufacturing, the subtractive manufacturing which we use this is basically a top-down approach. So what we have initially is a block. It could be a billet or any other shape, and then we use different kind of machining operations to give it a final shape. And in turn, we are getting a lot of waste materials. Okay, or even sometimes more than the material that is used for the shaping. And instead of that, we have come across with a specialized manufacturing technique, which is nothing but additive manufacturing, which on the other hand is the reverse of the subtractive manufacturing. So this is a bottom-up approach. We excuse me, we start with the powders, and then we slowly build the whatever shape is required layer by layer in an additive fashion to get the final shape. So here also we are getting the same shape as a subtractive one, but as you can see, the waste here is very much less, and even the remaining powders can be used for any other kind of shape. So we are quite gaining, especially in terms of not only getting a complicated shape, whatever we want, but also in reducing the waste. Okay, so this leads to additive manufacturing as our main focus, to explore more and more about this. And first of all, we need to find out or we need to emphasize on the basic differences between the subtractive manufacturing, which have been practiced for years, for decades, and people have gathered the knowledge, whatever required so far. We understand almost everything about the subtractive manufacturing. In comparison, additive manufacturing is new in the field, and there are many things that we need to explore before fully utilizing its capabilities. So these are the differences between these two techniques, which has been summarized. So first of all, additive manufacturing, as the name suggests, we are getting this by adding layer upon layer. Whereas in case of subtractive manufacturing, we are removing it from the prime block. Okay, so complex and customized shapes can be built in case of additive manufacturing, whereas in case of subtractive manufacturing, it is sometimes very much challenging if we have a very complicated shape to form. We also have some control on the porosity and the microstructure in case of additive manufacturing, which somehow we do not have, especially for metallic materials. We do not have that kind of precise control to get the density or the required porosity in a material. And as I mentioned, there is a significantly reduced material wastage in case of additive manufacturing, whereas we have quite a lot amount of material which are being wasted as chips, scraps, etc., which are completely making it even uneconomic. And but then again, also, so if we can simply highlight the advantages and disadvantages, we can say that this blue points here are actually the advantages of the additive manufacturing, which comes under the disadvantages for the subtractive manufacturing. Okay, so if we are trying to find out the pros and cons, we are seeing that the additive manufacturing is gaining by these 3 points, which are completely in favor of machining a material or manufacturing a material by the additive technique. On the other hand, if we are looking for the cons, then the prime cons for the case of additive manufacturing is that this process is applicable so far has been explored on only a few number of materials, a very narrow range of materials. Whereas, as I mentioned, that subtractive manufacturing we are practicing for decades. So we have used it for almost all kinds of materials. Whatever need to be machined or manufactured, we can do that on the basis of subtractive manufacturing. Whereas our knowledge base is still a little bit poor, or we are still lacking knowledge on a wide variety of materials in case of the additive manufacturing. So going further on the additive manufacturing, the advantages and the challenges of this are mentioned here. So first of all, we can do this in a single process. Okay, we can also do this remotely. So we do not need to have different kinds of setups for manufacturing different kinds of shapes. We rather can do this in a single step, and that shortens the supply chain, that makes it efficient, fast, and sometimes cost effective also. It reduces the material wastage, and that makes it more environment friendly. And more than making the component, additive manufacturing is also vastly used for all kinds of repair works. Okay, so we do not need to replace the entire component, or we simply can repair the necessary part by additive manufacturing, and we are good to go. So that also leads to, that also makes it often much more economic. And freedom of application. So we can do it even remotely. We can do whatever shape we want. We do not need different kind of instruments for different kinds of machining operations and so on. And as I said, that I, being a metallurgist, we always focus on understanding how the properties evolve. And for the understanding of the properties, it is very important to understand how the microstructure evolves. Okay, so additive manufacturing is known to produce finer microstructure because of the different kind of manufacturing parameters that are being used, the high energy source. We often end up with having a finer microstructure, and that leads to the properties which are often improved compared to the conventionally manufactured one. We are also able to produce functionally graded materials by additive manufacturing. Whereas in case of, let's say, as-cast components, there is a lot of microstructural heterogeneity that is forming anisotropy, and that leads to poor property formation in the case of the additive manufacturing, which are not being controlled properly. Okay, so these are the various steps of additive manufacturing, which you might have listened to some other talks so far. So it basically relies on computer-aided design, where we use this kind of designing software to get the final product shape, and we convert that to a STL file, which is being used in the machine, and use different kind of parameters, the different the materials that we're using, the energy source, power that we are going to use, scan rate, etc. All this we can specify, we can vary based on our need, and within a single go also we can keep on varying this if that is a requirement. So we have a lot of flexibility in modifying the parameters, and based on this, we end up getting the final product. And once we get the product, we can remove it from the substrate, and we are good to go. We can directly use it for application. Okay, so there are different ways of manufacturing different kind of materials by additive manufacturing. So there are this VAT photopolymerization, material jetting, binder jetting, all these are primarily used for polymers, etc. And material extrusion, sheet lamination, and these are also used a very less amount for metals, but mostly for polymers and something like that. For metallic materials, we primarily use these two techniques, powder bed fusion and powder feed fusion. So there are again different kind of techniques under powder bed or powder feed. Powder feed is also known as direct energy deposition. So we have different kind of ways by which we can manufacture metallic components using these methods. And the sources, the prime importance for additive manufacturing is the heat sources or the energy sources, and this could be anything like laser or electron, plasma arc, gas metal arc. These are some of the sources that are very much used for additive manufacturing, and among this, laser beam is the most widely used one. So coming to this two technique, once again, powder bed and direct energy deposition, also known as powder feed. There are different kind of process like direct metal laser sintering, electron beam melting, selective laser sintering, selective laser melting, etc. So basically what we have here is we have a stretch of powder over which we have the energy source flowing, and then the powder nozzle also, and we use the CAD design to get the particular shape. The laser is moving along that design, and we are getting the final shape. Similarly, for the direct energy deposition, also here there is no powder bed, but the powder is actually feed at the time where we are imposing the laser as well. So there is these are the powder nozzles. In this case, as you can see, there are dual powder nozzles, and we have the laser beam coming from the center, and then this moves as per the design of the CAD, and we can get the final material, final component that is formed. So to elaborate this a little bit more, I am going to show you two simple videos of these two techniques, one from each I have chosen, which are mostly used. So one is the direct metal laser sintering, popularly known as DMLS, and one is from the direct energy deposition. I have chosen the laser engineered net shaping as lens, popularly known as lens. So let's just have a look on how the powder bed process works. So this is the DMLS technique.
Direct metal laser sintering, also known as DMLS, is an additive manufacturing technology that creates metal parts directly from 3D CAD data without the need for tooling. DMLS utilizes a variety of metal and alloy materials, such as stainless steel, cobalt chrome, and Inconel, to create strong, durable parts and prototypes. DMLS is an excellent choice for functional metal prototypes, high-temperature applications, and end-use parts. The DMLS process begins in the same fashion as other layer additive manufacturing technologies. A program takes 3D CAD data and mathematically slices it into 2D cross-sections. Each of these sections will act as a blueprint, telling the DMLS machine exactly where to sinter the metal material. The data is then transferred to the DMLS equipment. A recoater assembly pushes powdered metal material from the powder supply to create a uniform layer over the base plate. A laser then draws a 2D cross-section on the surface of the build material, heating and fusing the material. Once a single layer is complete, the base plate is lowered just enough to make room for the next layer. More material is raised from the cartridge and recoated evenly upon the previously sintered layer. The DMLS machine continues to sinter layer upon layer, building from the bottom up. As the part is built, support structures are added to give supplemental strength to fine features and overhanging surfaces. The completed part is then removed from the base plate and treated with an age-hardening heat process to further harden the part. Any support structures are also removed at this time. With numerous surface treatment and hand polishing options available through service providers, DMLS parts can be used in highly cosmetic applications. Typical uses for DMLS include tools and manufacturing aids, small integrated structures, dental components, surgical implants, and aerospace parts.
Okay, so that is how a material component is being made by the powder bed process. As you can see that at every step we have a bed of powder and then the laser moves. So now coming to the laser engineered net shaping, which is the powder feed technique. Let's see how does this work. So this is how the lens system work from one of the companies which are the manufacturer of the lens system. So this is Optomed. And what we have here are the dual powder feeders here, 2 powder feeders. This is the control system. So it has been shown a repairing process here. You can see that we have the laser, we have the 2 powder feeders, and these are scanning along some particular direction to and fro or back and forth. And once we complete one layer, usually this is being shifted by 90 degree, or in this case it is being shifted by 90 degree, and the next layer is being formed on this 90 degree turning, so that we can have an even microstructure at the end of the process. So every alternate process we are changing the direction, and this can be depending on whatever is the final requirement. We can have the different parameters set. Once this is done, this is just simply removed and can be used. Okay, so as you have seen, there are different varieties of materials, all metals and ceramics and polymers that can be built by additive manufacturing, and there are different kinds of techniques of additive manufacturing which can be implemented. But when coming to the metallic system, we have seen that there are only a few metallic systems which are mostly being used for additive manufacturing. In almost the different sectors which are using, they are primarily dependent on this kind of materials. Okay, so aerospace field is the one which aerospace and medical, I must say, that these two are the industries which are exploring a lot on additive manufacturing, because these two are the fields which can which are having quite a lot of fund also to investigate, to explore the different properties and whatever the advantages of additive manufacturing to a lot extent. Apart from them, energy is also a very important field where additive manufacturing is being used. Automotive is also taking up a major role in case of this additive manufacturing. Marine is also, and by which anything, not only of this particular industries that are looking forward to additive manufacturing or are directly using it in applications, there are anything which requires a lot of machinability, weldability, etc., are slowly and eventually turning on more and more to additive manufacturing. Anything which requires high temperature application or corrosion resistance are moving also towards additive manufacturing to avoid the risk of different kind of processes that we are used for subtractive manufacturing. Instead of that, additive manufacturing are beneficial for such kind of applications also. So even tools and molds which are made of very, very hard materials, which are difficult to machine by conventional processes, there are ways by which we can make these materials, but these components based on tool steel or any other kind of materials which are primarily used for tools by additive manufacturing. Okay, so if we are looking at the different kind of materials that are being made by additive manufacturing, we have seen that stainless steel is the one. So if it comes to metallic system, stainless steel always takes the lead in any kind of applications, right? So we see that the stainless steel is being used for all this kind of applications, and a lot is being studied on stainless steel on the additive manufacturing sector. And in today's lecture, I'll be also discussing about the different forms of stainless steel and how additive manufacturing can be beneficial. Okay, apart from that, there are titanium, superalloys, aluminium is also being used in some ways, particularly in aerospace, where additive manufacturing plays a big role. Okay, so coming to that, again, as a metallurgist, our viewpoint is a little bit different, or maybe I will say complementary to what the mechanical engineers think of additive manufacturing. Okay, while the mechanical engineers are primarily focused on the manufacturing parameters, we are actually more concerned of what kind of properties this material is going to deliver. And we have seen that in case of additive manufacturing, there is a modification in the microstructure. So how does this modification generates, or how the microstructure evolves, is something is of our concern for the AIM component. Okay, because we are primarily want to determine that how the properties will be, and microstructure is very much connected with the properties of a material. So even though we know all about the microstructure and property of this material, let's say a steel, a component made of steel, we know all the microstructure and properties of that particular component made by conventional manufacturing, we are still not sure about how the microstructure and properties will be in case we are additively manufacturing it. Okay, so that leaves us to a huge responsibility and of course a huge scope also to explore more and more on the microstructure and property generation of the materials, which are even very much well studied for conventional manufacturing. But we have seen that in case of additive manufacturing, the same material, the same component shape can behave differently, can have different kind of properties or deformation behavior if we are using the additive manufacturing technique to prepare that. So in today's talk, I will emphasize on particularly on this aspect. Okay, so before we go on, let's just give you a brief idea for those of you who are not very much familiar with the metallic system or with the material system in general. Let's have a brief idea of how the microstructure, what do I mean by microstructure of material? So what we essentially have are the grain structure. Okay? In any material, we are particularly having a polycrystalline material. We are having this grain structure where each of these grains are oriented along. These are nothing. Each of these grains are nothing but the crystals, and that are oriented along different directions, separated by a boundary. Okay, so to give you some examples, this is an austenitic stainless steel, and you can see the austenite grains here. So each of these are different grains, and the different orientations are also giving it different colors. Now there could be different phases also. Okay, as you can see here, this is a duplex steel where we have two different phases, austenite and ferrite. So this little lighter shade color is for the austenite, and the darker shade, the gray color, is the ferrite. And you can see that these are uniformly, in this case, uniformly distributed. Depending on the material, these are distributed in the structure. So this is titanium, and here also we can see a single phase. These are grains, as you can see, but we also have twins. Okay, so twins are something that we need for deformation. So titanium is a hexagonal structure, usually have these twins as their main source for deformation. These are aluminum, and this is a welded part, and I have shown this to make you understand that there could be differences in the microstructure. Okay, you can see that there are fine grains and we have coarse grain here, but all this is fine, or the coarse are still equiaxed, means is a more or less like circular, equiaxed, almost have aqueous grains, whereas in some cases, in some places, we can have the columnar grains as well, as you can see. Okay, now differences in the grain size and morphology can also lead to variation in the properties. This, for example, is a pure copper, and this one is having the copper alloy, which a different phase, which is having much more higher hardness. So eventually the properties, the entire properties of these materials are dependent on the variation in the grain structure, shape, size, and morphology, as well as the presence of different phases in the structure. Okay, so based on this, what we can, this is a very famous microstructure property tetrahedra, which explains that when we have some kind of structure, this can be having different kind of properties. Okay, and the different kind of structure can be obtained by varying the processing conditions. Okay, be it conventional or be it additively manufactured. If we vary the processing parameters or processing conditions, we end up having differences in the structure. Structure here means microstructure. And if we are varying the microstructure, we end up having different kind of properties. And if we are having variation in the properties, that leads to completely different performance. So based on our performance requirement, we actually kind of tailor all these factors. Okay, we plan, we design our processing conditions in such way that we can end up having the required performances. And the one sitting in the middle of this tetrahedra is the characterization technique, which we use different kind of characterization to understand the relation between all these four. So these are very much related, and we cannot jump into one of this by bypassing the others. Okay, so this is how these are being related. So ultimately, we can say that processing is related to performance. Okay, these are the steps by which we can achieve that. Okay. Now, these are just being elaborated. So if we use different kind of processing techniques, solution and quenching and hot isostatic pressing, even additive manufacturing, powder atomization, etc., we end up having differences in their phase structure, their grain size, and there are different others, the phases and even defects, the inclusion, segregation that are forming. All these are primarily affecting the properties of the materials, like the strength, ductility, toughness, fracture, fatigue, or whatever are of significance for any particular application is related to that. Now, when it comes to additively manufactured products, so this so far is applicable for any kind of material processed by any kind of technique. Okay. Now, while coming to the additive manufacturing technique, what we are concerned of is the heat and the energy that is being generated is not uniformly distributed. Okay, so as you can see here that it is basically forming a loop of varying temperatures. Okay, so heat distribution is not uniform, and that also varies from layer to layer. So there are differences in the temperature, the red one being around 1928, whereas the blue one is having a temperature of 1500. So 400 differences in temperature of 400 Kelvin is just when we are using this additive manufacturing technique within a layer. And then with layer by layer, as you can see that this is being shown for layer by layer, these loops are also changing. Okay, and as a result, of course, if we are having variation in the heat generation and as well as the cooling rate, so you can see that the cooling rate also varies with the layer numbers. Okay, we are having fast cooling at one places, whereas we can have a slow cooling in the different layers. And as a result, all this, the heat distribution as well as the cooling rate is affecting the microstructure in a big way. We are having finer grains. Depending on if the cooling rate is higher, we end up having finer grains. If the cooling rate is lower, we end up having coarser grains, and so is for the heat distribution. So as a result, we are having variation in the microstructure all throughout, and that will lead to the properties variation also. So I'll go through that slowly, but this is an example of how the variation in the microstructure can end up in an additively manufactured material. So we end up having a inhomogeneous microstructure. There could be different kinds of grain structure that are forming. We can have a dendritic structure, but equexed. We can also have columnar grains, cellular, or also planar structures. So all these different kind of structures can form if we are having this variation in the heat flow. Okay, this is just an example of something that we are seeing here. We are seeing the equexed grains on the top and examples of the columnar grains which are forming in between. Okay, so we can have, due to additive manufacturing, a modification in the microstructural size, morphology, the phase that are being formed, as well as even a variation in the composition. So although we started with the same powder of the same composition, we can have differences in the composition all throughout the structure. Okay, so this is something being shown schematically as well as by characterization also, that how the grains vary at the different layers cut across different planes. So you see that this is the building direction, this is the top and the bottom, and there are variations in the structure. You can also see the layer by layer manufacturing process, the signatures for that. And if we look at the different sections, we can have differences in their structure, differences in the microstructure altogether. Okay, so that will lead us to investigate more and more that how this the microstructure is being varied. And if we are always control freak. Okay, we the engineers always try to engineer things, tailor things as per our requirement. So when we understand that there is a microstructural inhomogeneity, our next target is to control that inhomogeneity so that we can have different kind of microstructure, but we would like to have those different kind of microstructure at the places that will benefit us the more. Right, so based on that, several studies has been performed to work on optimizing the process parameters. Okay, so that we can have the different kind of microstructures that will finally lead to an improved properties. At the end of the day, we are all eager to develop a material, develop a component which are having a better performance than its predecessor. Right, so not only that, now we also need to know the pros and cons of any kind of technique, right? So when we say that we want to control the microstructure development, we should also understand the risks of that technique, the risk in this case, the additive manufacturing, and what kind of microstructure as well as microstructural defects it can form. So these are the very typical of the hot tears that generated the balling effects, and there could be some unmelted parts that are forming, which can act as defect during any kind of mechanical testing or mechanical stress application. These are the very typical structures of additively manufactured component, where we have this fish scaling kind of structures. These are called hatches, and we can also have hot tears. So there are cracks in between the structure, and which can completely lead to failure of the component at a much more lower stress than expected. Okay, so with this very basic idea about how the microstructure will be inhomogeneous and how that can lead to variation in the properties, we'll move on to a few examples of the the additively manufactured systems to understand the microstructure property correlations in all this. Okay, so we start with some non-ferrous materials which are of interest. Titanium is been very widely used and already in service for aerospace industries. And then we will also discuss something on the nickel titanium based shape memory alloy, which is a prime material for biomedical application. Okay, and of course, as I said, that when it comes to metals, we know that steel is something that are very widely being used in all different fields. So we also have selected two different steels. One is a biomedical grade steel, and another one, this 15.5 pH, is a tool steel of very high hardness. Okay, so let's start with the first system, a titanium alloy, and this is a titanium 6 aluminum 4 vanadium. Now, amongst the titanium alloys, different kinds of titanium alloys, Ti6L4V, or commonly known as Ti64, is the very widely used one. Actually, the most widely used one of all the titanium alloys. This material is used for aerospace application, for biomedical application, even for automobile application, marine application. So these are so much in use. And of course, additive manufacturing also is being explored widely on this material. So this is the macro structure done at a very high magnification. The scale bar is not visible here, but if you can see what my mouse is pointing, this distance is 1 millimeter. Okay, so we can see the macro structure, and you can see this patches, this layers actually. So these are the signatures of the additive manufacturing technique. And if we look into the microstructure, you can see that there are variations in the grain size. So if this is the building direction, this is the top and this is the bottom. Microstructures has been characterized at the different sections from B, C, D, E, etc. You can see that there is a complete variation in the microstructure. The grains here are lamellar, okay, with much more higher size, whereas the one at the top is having much finer grains and almost equexed kind of grains that are being formed. Okay, so the grain size, morphology, in this case also we can see the lamellar, and this is the EBSD of these two, where we can see the phase fractions also. The red one is the alpha phase. Now titanium, this particular alloy has two different phases in it. One is the alpha phase, which is having a hexagonal structure, and one is the beta phase, the green one here, which is having a BCC structure. Okay, so you can see that there are variation in this from the bottom to the top, as well as there is variation in the microstructural size as well. Okay, the picture below here with different colors, this shows the grains of different orientation. So grains are randomly oriented in all cases, but we can see that the size is varying to a large extent. Now, if that happens, let's say we are getting a variation in the hardness also, right? So this is the Vickers hardness that is being plotted, and this is the top and this is the bottom. And you can see that from bottom to top, even from bottom to top, we are having a significant variation in the hardness, something like around 500 HV to around 650 HV. Okay, so that's not a small amount that we can ignore. So that means that within the same component itself, based on the building direction, we can end up having variation in the hardness. And we have to keep this in mind while we are using this for any particular application. Okay, by the way, at any point, we can see that this is something, this is the hardness around 400 HV for the Ti64, which are being conventionally produced. Okay, so additively manufactured, be it even the bottom or the top, is always having higher hardness. Okay, the structures that are forming usually are much finer than the one that is being formed by the conventional machining, and this is all related to the heat flow distribution. Okay, so eventually, due to additive manufacturing, we end up having improved mechanical properties of the material in most cases. Of course, there could be an anisotropy in the properties, and that has to be used wisely while we are using it for any application. So What we have seen from here is that there is a variation in hardness along the building direction, as well as highest hardness is seen for the EQX microstructure. This is being properly explained in this paper in more details. Now, this is a separate study on this TI64 itself, and what they studied is that if we are varying the process, once by lens, which is a powder feed process, and another one is being prepared by SLM, selective laser melting, which is a powder bed process. Okay, so if we vary the process starting with the same powder, then also we end up having variation in the properties. So this is for the same magnification. This is the low magnification micrographs for the lens and the SLM processed TI64, and it looks like that the lens one is giving us the finer structure, because we cannot particularly resolve it even at this magnification, right? If we go for higher magnification and look into it much more closely, we'll see that the SLM actually produces this fine acicular structure, which are nothing but the martensitic structure. Now, martensitic phase has a completely different properties, usually with high hardness. Okay, so that leads to variation in the mechanical properties also. So although we have used the same powder and even the same technique as additive manufacturing, but just by varying the particular techniques as powder bed or powder feed, we end up having variation in the microstructure, and that will end up giving variation in the properties. Okay, you see that this is the typical tensile curve, true stress, true strain curve, and you can see that the SLM is having much higher hardness and much higher stress, UTS, ultimate tensile strength, compared to the cast or the lens one. Okay. Now, within a particular process also, let's say we are using lens or we are using SLM. There also, if we are varying the processing parameters, we can end up having variation in the microstructure. So in this case, the top two images, let's say, we have used the same power of 200 watt and the same scan speed also, but there is a variation in the powder flow rate. Okay, powder flow rate is higher for this one, which leads to higher coarser microstructure, coarser grain size, right? On the other hand, if we are comparing the one here, the right one on the top versus the bottom, we see that in these two cases, we have varied the powder flow rate in both these are same, but we have varied the power as well as the scan speed. We have reduced the power as well as increased the scan speed, and we end up having even coarser microstructure. Okay, so and not only that, not only the microstructure, but we are also sacrificing on the density. Okay, so if we want to achieve improved density, because we finally, for any particular component, we need to have as higher density as possible to get rid of all the pores and voids. In most of the cases, these are not preferable unless we want a porous structure for some specific applications. We want to have our density to be maximized, and this maximized density can be achieved if we use higher power, lower scan rate, as well as lower powder flow rate. Okay, so we need to use a combination of all these parameters to achieve an increased increment in the density, and that will lead to improved performances and least chances of failure as well. Okay, so you can see that this is the density that are forming by this lens and the SLM process if we are varying the energy density. Okay, now combination of these things will, these parameters like power and scan rate as well as powder flow rate, this combination of this will lead to different values of energy density that we term as, right? So if we vary the energy density, basically the relative density also varies, and we end up having higher density if we keep on using higher and higher energy density during the preparation process itself. Now, based on two different techniques, again, powder feed versus powder bed, we see that the density of around 99.5 or 99.9% can be achieved if we use energy density of only 120 joule per millimeter cube for the case of SLM, whereas the same kind of density can be achieved if we use much higher energy density of around 140, 150 in case of lens. Okay, so by varying the different kinds of additive manufacturing technique also, basically we are varying this energy, the density that we are achieving based on variation in the energy density, and that will end up having variation in the microstructure and properties. So you see that for the case of lens and SLM, if you are using low energy density of only 105, we can see that there is lack of fusion. This will be considered as defects. This will be considered as lead to crack generation and lead to early failure. So we cannot use this for practice. We have to, while preparing the component, we have to use higher energy density, and we can achieve a completely dense structure if we are using particular energy density for the different process. And we can see here that SLM is beneficial in that regard, that we can use this, we can achieve the same amount of density, and that too with the formation of martensitic structure that will lead to higher hardness and ultimate tensile strength, even by using low energy density. And low energy density, the industry people will read this as lower cost of production. Okay, lower time of production, so that will be much more efficient. Okay, so we need to know all this information before we can use this for any practical purpose. So this particular paper here shows that how the properties, particularly the strength, ultimate tensile strength, in strength, and ductility, elongation to failure, how these are varying for the different kind of processing techniques. This includes the cast, the typical conventional technique like the cast, forged, annealed, etc., and the different kinds of additive manufacture technique also. And all these properties are being very nicely compared, from which we can have an idea that which one, which technique to be used for any particular application. Okay, so application requirements are different. We do not always strive for higher strength. We also have to look for the typical ductility for failure, and we prefer to have a optimized or a combination of higher strength and ductility, right? Okay, so overall from this series of studies, we have understood that microstructure and properties do vary along the build direction, and different AM processes as well as the process parameters influences the microstructure and properties differently. Okay, so with this, let's move on to the next non-ferrous alloy, which is popularly known as Nitinol. You must have heard about this name. The scientific name is nickel titanium. It usually is an equiatomic material, alloy metallic system, which has almost 50% nickel atomic percent, 50 atomic percent nickel and 50 atomic percent titanium. And why we are interested in this particular material is that this is having very unique kind of property. Okay, the common name that we use apart from Nitinol is, it is called shape memory alloy. It can memorizes its shape, right? So, and this happens because there are a change of phases that happens. So it initially has a cubic structure which changes to a monoclinic structure by the application of either stress or reduction in temperature. Okay, so based on this phase transformation, this leads to some unique, different, completely specialized properties that we can achieve. So what it does is, it has the austenite structure initially, which due to application of stress converts to martensite. And if we keep on stressing, it leads to a huge amount of deformation, which can be completely recovered. Okay, so unlike any other system, any other metallic system, which can recover only up to this amount of strain, this particular material can recover this entire strain value and come back to the initial phase. So this is what is called pseudoelasticity. It is like elasticity, but it is not exactly elasticity. Rather, it happens due to phase transformation. That is why it is called pseudoelasticity. And if we do the stress strain curve, we see a curve like this. So this entire plateau strain and this elastic strain can be completely recovered, as you can see here. Okay, a strain of around 10 to 15% can be completely recovered, whereas in case of normal metallic materials, the strain that can be recovered is often less than 1%. Okay, so that gives us makes us interested on this alloy, and the same kind of features can be also achieved if we are just changing the temperature. Okay, if we are simply changing the temperature, we can see that there is a phase transformation that is happening, and we can also achieve similar kind of behavior. It can memorize such shape. That is why it is called. Okay, so based on this, it is very much used in different application, and one of the niche application is in biomedical application in the form of stent, cardiovascular stents. Okay, if we have a blockage in one of the arteries that leads to our heart, we often need to put that stent. It has become very common these days where we need to use such stent. Okay, so let's just see how it works. So you can see that there is a clot here due to cholesterol or any other junk, and the blood flow is restricted. So if we put a stent here of nickel titanium, it can expand based on the pressure the artery gives as well as the temperature, the body temperature, and it removes the clots to some extent, and the blood can flow easily. Okay, so this movement of the stent is ensured by the high pseudoelasticity of this material. Okay, so what we have done in our group is that we prepared this material, nickel titanium based material, by using LENS, laser engineered made shaping technique. Okay, I already have shown you how the system works. So this is a powder feed system, and we use the different processing parameters like the laser power, scanning speed. We have altered this, and we have ended in having 3 different energy densities. Okay, the lowest one is around 27 joule per millimeter cube, and the highest one is 70. Okay, so almost 3 times that. So based on this, we see that now, so this is the component, the schematic of the component that is being formed, and we had initially done a microstructural study. Okay, so we have studied the microstructure at the different sections: top, middle, bottom, cross section, as well as the innermost areas in the build direction, along the build direction, perpendicular to the build direction, parallel to the build direction, etc. And we have seen that this is how the microstructure looks like, the different grain colors here. So these are simply optical micrographs, okay, color tint etched micrographs, which shows the different orientations. But you can very well see, this is the EBSD, you can very well understand the layer by layer formation procedure based on this. Okay, now if we look into it into more details, we see that this has this typical hatch structure. These are formed because of the movement of the laser. Okay, so this kind of circular loops are being formed, and there are different grains that are different morphologies of grains that are formed because of the heat distribution, as I have explained earlier. Okay, now if we look into this more closely, we actually have determined the layer thickness as well as this hatch diameter, etc. And we can also figure out that there are different kind of grain structures that are forming. We have columnar structure here, whereas we have coarse equexed, we have fine equexed, and so on. And the sizes are also vary to a large extent, whereas the fine equexed has around 4 micrometer size. The equexed, the coarse equexed is having around 25 micrometers. So there is a huge differences in the sizes. Okay, we also have found out the porosities in the material. We have done a 3-dimensional microcomputational tomography to see how the porosities that are generated. Now for biomedical applications, often we need a certain amount of porosities in the material because of some biological requirement. Okay, so this is for one material, and this is for the 3. So we use 3 different energy densities, and you can see that if we use a lower amount of energy density, we generate having a much higher number of pores. The pore volume fraction is much more higher, and the pore volume fraction reduces if we uses higher density. Okay, so then the next thing we wanted to study is the phase evolution, and here also we have seen that the one prepared with the highest density develops some different kind of phases, which is a precipitate phase, which is seen here by the TEM evolution, as well as the martensite phase. Some amount of martensites are also seen here, which are not seen for neither in the powder or in the other two alloys prepared with moderate or lower energy densities. Okay, we have characterized the DSC, differential scanning calorimetry, to find out this transformation temperatures, and there also we have seen that these temperatures are varying significantly. The one which is prepared with a higher energy density is having this temperature quite higher than room temperature. So this means that the properties will vary, and the pseudo elasticity is going to affect by this temperature itself. Okay, so we actually, so far from the microstructure and phase analysis, we generated some idea that this one, the one prepared with the highest energy density, is a little bit different from the other two in terms of having different phases and the precipitates and the transformation temperatures. Okay, so next we wanted to figure out the mechanical properties. We started using macro indentation using high amount of load, and we see that there are not much difference in the hardness that is generated. Okay, moving on to the micro and nano indentation. In case of micro indentation also, we have seen some differences in the hardness, particularly for the E2 and the E3 thing, which becomes much more clear if we do the nano indentation. So we are now probing a very small volume fraction. Okay, so the property changes that are forming is getting apparent from this kind of studies at a very precise level. Okay, so what we can figure out from here is that the presence of martensite and the precipitates, those enhance the hardness and elastic modulus for the alloy prepared with the highest energy density. We are not done yet. The next thing we did is nano indentation, but we use a different kind of teeth geometry. And you can see that the red one is the one with the highest energy density, and the black one is the one with the lowest energy density, and the green one is the moderate one. Okay, now we wanted to figure out the pseudo elasticity, right? So how much strain it can recover, and this can be found out from the nano indentation pH curve itself. Okay, this green part here signifies the pseudo elasticity. So we estimated that as a remnant depth ratio, and we have seen that E1 and E2, the one prepared with the lowest and the moderate one, are having very high amount of pseudo elasticity. Okay, lower the value of this RDR, higher is the pseudo elasticity. And we have seen that the highest is for the one prepared with a moderate energy density. But so far, we understand that E3, the one prepared with the highest energy density, may have a higher hardness, but that is not good for giving us lower pseudo elasticity. Okay, we still do not have a complete picture, and we tried to figure out this by a very unique method that our group has generated to get the stress strain curve out of nano indentation. And from here also we can see that the E2 is something which shows some kind of strain plateau, which means that the pseudoelasticity is active in this particular material. Okay, so to get even a clear picture, we did the conventional tensile testing, and we have seen that the E2 has a much more, not only the strain plateau, but we have a much more higher ductility for this case. We also have done this in like the cyclic tensile test to see how much load, how much strain can be recovered, and we see that the green one here tops. Sorry, the blue one, the E2 is the blue one here, which tops here. And we have done this with the digital image correlation to get a more clearer picture. Overall, what we have figured out from all these studies is that although we started with the same powder, right, we just vary the process parameters, and we have seen that we need only a particular amount of energy density, an optimized value of energy density, to achieve pseudoelasticity. If we are not doing that, we will end up having a material which might be hard, but which is not pseudoelastic. So required pseudoelasticity can only be achieved if we use that particular optimized parameters. Okay, so any questions so far, or I can continue? Okay, fine. So let me just go ahead with the steels that we have in the store. So the first one is a 316L steel, very widely used for different kinds of applications, including even biomedical applications. So it has the higher corrosion resistance, which is why this is being preferred in various kinds of, and especially also for biomedical application, even marine applications and so on. It has higher machinability also. It has several solution strengthener that increases the strength and hardness of the material. It has a higher toughness also even at low temperature. So these are some of the properties of 316L steel, which makes it usable for biomedical application, not only as implants, also these are used as implants, as you can see, these are the examples of the hip implants and the for the femoral fracture, as well as these are used for surgical tools also. Okay, used as pipes and in even also marine application and so on. Okay, so what we did is, in this case, we have used a LMD based manufacturing technique. Okay, and so this is a laser metal deposition, and we got a block something like this. So this is the substrate here, and the top one here is the block that we have prepared by LMD process, and we cut it into several sections, as you can see here, to get the cross section, and to study the microstructure at the top and bottom and along the build direction and parallel to the build direction and so on. Okay, now this is the macro structure. Once again, we have collected hundreds of optical micrographs and we have stitched those to make a montage. And you can see that this is very clearly evident that how the layer-wise additive manufacturing process has been formed. And if we look closely into that, we can identify the hatch structure, and we measured the hatch spacing, the layer thickness, etc. So these are some of the layers. So this is the substrate here, the black one. And then if you can just look into the layers one by one, you can see that the microstructure varies to a large extent, right? So we can say columnar grains here, we can see very fine grains here, the one which is near to the substrate because of the differences in the cooling rate that leads to such kind of variation in the properties. And the higher magnification shows us this even more clearly about the variation in the microstructure. Now, what we have done along with this is that, so this the AB here stands for the as-built one. What we have done is we applied the conventional heat treatment procedure to the additively manufactured one. Okay, so we prepared this by additive manufacturing. So we have the benefits of additive manufacturing, and then we simply solutionized it to get a uniform microstructure. We already have figured out from this structure that from these studies that the microstructure is too much inhomogeneous. So we did a solution treatment. And what we end up is having a very much homogeneous microstructure all throughout. Okay, and we did the phase studies also to see that there is no changes in the phase structure because of the solution treatment. So that means that we are good to go, at least in terms of the microstructure. Okay, now we did the mechanical property evaluation. Hardness at different levels. We have done micro, macro, and nano to find out the variation in the hardness at the different layers at the top, middle, etc. And also in the as-built condition as well as the heat-treated condition. And what we can see here is that from the bottom to top, there is not much differences in the hardness values. Rather, we have some differences due to the solution treatment part. Okay, and we can very well figure that out from the tensile test. So we have done the tensile test, and you can see the bottom one here. The square indices are for the solution treated one, as well as the circular ones are for the as-built one. Okay, and we can see that the solution treated one has a little bit lower amount of hardness. As I said, that the additive manufacturing has its own benefits, and it end up leading us to finer microstructure overall that leads to higher hardness. But when it comes to the inhomogeneous microstructure, that also is associated with lower ductility. That is what we are seeing in the as-built one. Okay, if we are solution treating this, we are getting a homogeneous microstructure where the strength decreases to some extent, but we also acquire a very high level of strain to failure, ductility of around 50%. Okay, this is a typical fractograph showing the dimples, which are evident for a ductile failure. So overall, we understand from this study is that we can use the conventional heat treatment procedure, especially the solution treatment, to get rid of the microstructural inhomogeneity and end up having the property requirement, optimized property of high ductility and moderate strength, which is well below, well within the limit that is being used for practice. Okay, the details can be found in this paper here. Okay, coming to the next steel, which is, as I mentioned, is a precipitation hardened steel. So this is a tool steel. We can use this for a tool steel purpose. Okay, this is usually a hard one and difficult to be machined conventionally. So that's why there are a lot of studies are being done on this category of steel, the precipitation hardened steel, where we can figure out how the properties of this material varies. So we made a shape by the DMLS technique. So it is, instead of a rectangular block, we try to give in a particular shape having a hole in it and variation in the diameter, etc. Here also we have evaluated the microstructure at the different phases, and you can see that at low magnification we can see the hatch structure, and then when we are going to the higher magnification, 10 times higher in this case, we can see that different kinds of grains are forming. We have the cellular structure, columnar grains, as well as we have perfectly equivalent grains in this case. Okay, and when we look at even higher microstructure, we see that there are some precipitates which are forming in this area. Now, in this case also, what we have done is to get rid of the microstructural non-uniformity, we have solutionized it. And not only that, this particular material, this precipitation hardened material, works best when we do some aging treatment. Okay, that aging treatment is to ensure the precipitates to form. So we actually performed similar kind of aging treatment that are typically used for conventionally cast material. We performed the same kind of aging treatment. So H900 here means heat treating at 900 Fahrenheit, and H925 means heat treating at 925 Fahrenheit. Okay, and we are successful in identifying the precipitates that are being formed. Some chromium-based precipitates are being forming, and we then did a detailed study, particularly on the phase formation. Okay, we have found out all those the precipitated structures that are being formed, and we also have generated the porosity analysis. Okay, for the as-built structure to see that how efficient the process is, additive manufacturing process is to generate the right kind of porosity in the material. And not only that, this material has a lot of application in certain atmosphere, which implies a corrosive atmosphere, right? So we tried to find out the corrosion resistance of this material, and not only in the as-built condition, but also in the solution treated, as well as the two aged condition, the heat treated at 900 and 925. Okay, and we figured out that the one heat treated at 900 has a much more improved corrosion resistance. Okay, so far we can only from the microstructure say that there are some precipitates forming if we are doing the heat treatment at particular temperature, but we also tried to figure out that what is the optimum heat treatment condition for an additive manufacturing to precipitation hardened steel to get the best combination in properties. And this job is not complete if we are not evaluating the mechanical properties. So that's what we have done next. We have done the indentation, nano indentation in this case, at the different sections. We have done this at top, middle, bottom, cross-sectional plane, as well as the solution treated one, the aged one, heat treated at 900 or 925 Fahrenheit. And we have seen that somehow this 900 one is giving us higher hardness. Okay, but this data, we still will not go with this data because this has been done on a very low volume fraction. We have done the nano indentation. So this gives us the picture of a very localized volume, right? And we cannot we cannot make a component at a large scale just based on these data. So the next thing that we wanted to figure out is we have done the tensile testing. So this is the typical tensile specimen that are being used, and you can see that once again we have done the tensile testing for the as-built one, the black one here, and then the solution treated one, as well as the two heat treated aged condition. Okay, and we have seen that the maximum yield strength is obtained for the one which has been aged at 900 degrees centigrade. Okay, so sorry, 900 degree Fahrenheit. So based on this, we also have figured out the strength at the different condition, and we can see that both the yield strength and ultimate tensile strength reaches the maximum if we are heat treating the as-built additively manufactured material to a temperature like 900 Fahrenheit to get the best combination of properties. It has a little bit lower ductility compared to the one at 925, but that together with the high strength, it actually gives to improved toughness. Okay, improved tensile toughness that we can see from here. And we also have seen a mixed mode kind of failure. We have seen some dimples as well as some cleavage in this case. So we can safely say that we can additively manufacture a precipitation hardened steel by this powder bed technique. And then if we are imposing the conventionally used aging treatment, we end up having even improved hardness, so that our hardness and strength, and with moderate and optimum ductility, so that we can use this for service. Okay, so overall from these two steel studies, we can see that the microstructure and properties do vary along the build direction. We have seen this based on the top and the bottom. And we can also see that the conventional heat treatment procedures, those can be imposed on the additively manufactured stainless steel components to homogenize the microstructure as well as to achieve the improved performances and isotropic performances, most importantly. Right. So with this, I would just like to end my presentation with a small video of the different kinds of additive manufacturing technique. So let's just go with this.
Of powders in situ and two systems for the heat treatment of the components produced. Additive manufacturing is a process enabling the production of solid objects in any shape and form, starting from a digital model through a process of aggregating materials, in this case metallic powders. An example of the great freedom in designing shapes and forms is the combustor injectors. This part, if made by casting, is produced with 5 pieces, which must then be joined together. With additive manufacturing technology, only 1 piece is produced. DMLS, direct metal laser sintering, is the most diffused and enables the working of many materials, using a laser beam to melt the material into the form foreseen. EBM, electron beam melting, sees Avio Aero as undisputed leader and the major expert worldwide in the manufacturing process applied to TAL. In this case, an electron beam is used in the melting process of the material. Among the raw materials used by Avio Aero for additive manufacturing is TL, titanium aluminide, an intermetallic material formed from titanium and aluminium. In the production that harnesses additive manufacturing, these materials are used in powder form. This allows the production of components with a particular performance, like, for example, airfoils for low-pressure turbines, designed for the hot parts of the engine where temperatures reach up to 740 degrees centigrade. The use of TL enables a reduction of about 50% in the weight of components, which means lower fuel consumption and therefore lower emissions. Products are uniform. Additive manufacturing guarantees metallurgical uniformity of the product. Mechanical characteristics are better. Pieces are more resistant. It is a technology that reduces emissions to the minimum. Manufacturing is carried out in vacuum chambers with no harmful exhaust emissions. Moreover, to make a product weighing 1 kilogram through casting, about 4 kilograms of material is needed, while only a maximum of 1.5 kilograms is used with the additive manufacturing technology. Less material, less energy, less emissions. Production times are greatly reduced, no longer months, but just a few days to produce the same amount of product at a speed of 50 cubic centimeters an hour. Additive manufacturing is a technology that responds fully to the needs of the aeronautical industry of the future, reduction in weight and the consequent saving in fuel consumption through more robust components designed and produced with greatly reduced times.
So this basically summarizes the importance of additive manufacturing that we've discussed so far. And of course, I would like to acknowledge particularly my students who helped me do all this work and also carrying forward this work. And then we have collaborators from all across the world, particularly from Germany and USA, who have supplied us some of the materials, and we have discussions at several occasions, and also from India, from the Central Glass and Ceramic Research Institute for the nickel titanium pieces that they have done from National Aerospace Laboratories and so on, BRC, BMRL, etc. So, okay, so just to inform you that we do have a Center of Excellence here at IIT Kharagpur, where there are several different opportunities which instruments that can be used. We do have an additive manufacturing system here and different other experimental facilities which are up for using. So thank you very much, and I'd be happy to answer if you are having any queries.
Ma'am, it's been a knowledge blasting session. So if you permit us, we will ask few participants to give their feedback directly so that you can also understand how well they understood your session, ma'am.
Right. I'd be happy to have that.
Yeah. Participants, you can just give your feedback orally. You can unmute yourself and switch on your videos, and you can share your feedbacks.
Good morning, madam. Myself, Dr. Puvadagan from SSN College of Engineering. Thank you, madam. It was a wonderful presentation. We learned a lot from your lecture. Madam, I am having some few doubts. The first one, is it possible to control the refinement of grain whenever we are manufacturing any metals or alloys by using additive manufacturing, because the mechanical properties of the material depending on the grains or size of the grain? Is it possible to control or tailor-made the grain size of the material by additive manufacturing?
Yes, of course. First of all, in additive manufacturing, as I mentioned, there is usually a gradient of grain size. Now, this also depends on, varies from materials to materials. But of course, we can, if we are varying the parameters, for example, the laser parameters, we end up having finer and finer grains. Absolutely possible.
Possible. Okay, madam, one more question. So when we are comparing the conventional casting, powder metallurgy and additive manufactured products in terms of ductility or toughness, where the additive manufactured product stands when comparing with cast product and powder metallurgy products?
Okay. Usually strength wise, as I said, that the hardness and strength improves for the additively manufactured materials. But toughness wise, toughness is related to ductility also.
Yes, madam. Yeah.
So ductility often, ideally, it should have even improved ductility because we are having finer grain size in most of the cases. But there could be some non-uniformity, and that also, once again, these are not a simple yes or no answer is not enough for this, because if you are varying the laser parameters, we can actually minimize. When you say additive manufacturing, the first thought that is coming to me is that there could be some defects that are forming, and we have to make sure that those defects are not forming. If those defects are being formed, then of course the toughness and ductility will be reduced to a large extent, right? So if we use the optimum parameters, processing parameters, we can end up having even improved toughness and ductility and strength all at the same time for the additive manufactured materials. That is our target.
So in some cases, if you are going to lose the ductility or toughness, then it is very difficult to get the formability characteristics. Then how to manage these situations?
That is what we have to do. Not only trial and error, but we also have to do it in a scientific basis to identify the optimum parameters. As I would say that these are the most important thing. That is why a lot of work has been going on additive manufacturing, and still we are focusing only a selected bunch of materials. Because we want to explore the things. Not everything is known, and there could be a lot of difference if we simply vary the parameters. Okay, as I have shown in my presentation also.
Yes, madam. Yes,
so,
yes, madam. Last question, madam. Actually, in the additive manufacturing, in some cases, we are using supporting materials. So whenever we are fabricating, but we are claiming that in additive manufacturing, wastage is less. But whenever we are using supporting materials or support structure, sometimes that will also go as a waste. Then how to, yes.
No, support structure, you can simply remove it, you can reuse it.
Reuse it. In all the time we can reuse it, madam?
Yes, support, so that is like a plate over which you're forming your structure, additively manufactured structure. And once done, you can simply remove the plate.
Okay, again, we can recycle and reuse it.
Yes.
Thank you, madam. Thank you very much.
Welcome.
Any other participant would like to ask question to ma'am?
Yeah, good morning, ma'am.
Good morning.
This is Krishna Kumar from VNRVJIT.
Hello.
Ma'am, which material can we compare for aluminum alloys, ma'am? Magnesium is better than aluminum alloys. Which material can we compare, ma'am, with aluminum alloys? For example, if I made aluminum alloy with boron carbide, aluminum with boron carbide, which one is better, ma'am? If I go for magnesium is better or aluminum is better?
And it completely, your question is not complete. It depends on what kind of application you are talking about.
Actually, I am making some composite material, ma'am, for corrosion resistant mechanical properties. For getting good mechanical properties, which material is better, aluminum or magnesium?
I will go with titanium.
Titanium. Okay,
titanium has a high corrosion resistance. Titanium is light metal, so yeah.
Okay, thank you, ma'am. Thank you.
Good morning, madam. This is Ankush Khansole from CV Raman Global University, Bhubaneswar. Madam, I am a research scholar currently admitted for a PhD. What is the thought process for selecting the material for additive manufacturing, ma'am?
Depends on the requirements. And when we say requirement, in my talk at one point I mentioned that aerospace and biomedical, these are the two industries which really have the money to spend on research, right? So most of the work, at least for the metallic systems, are being used for such materials which are used for such kind of application. Okay, so that's why you see so much on titanium. Even steel also, particular categories of steels are being used.
Yeah, ma'am. And if I have to select some particular material and this what problem occurred in aerospace, so may I have to introduce myself self material, or I have to take some reference from other papers, ma'am?
Can you once again, can you ask a question?
If I find out one problem which will be occurred in aerospace, and for that I have to introduce a new material, or I have to refer some the previously used material, ma'am?
we all work on previously used materials unless you are, I mean, designing a new material is very much challenging and it requires a lot of studies. So we go ahead with whatever is existing on knowledge base, and we try to move forward from there. So if there is an aerospace, you want to apply for aerospace application, you can see that there are a lot of work has already been done on different kind of materials, even on additively manufactured materials which are in service, like GE has launched the TIAL based additively manufactured components. Okay, and that aircraft is in service.
Yeah, and ma'am, one last question. Ma'am, for preparing, for writing the research paper, for drawing the graphs and editing some images, which software we will prefer, ma'am?
Writing the research paper, you have to use Microsoft. There
No, ma'am, for editing the graphs. Madam, I saw your presentation. These graphs are very good, and I'll also refer your research paper, ma'am. So
now there are Origin, Kaleidograph, so many graph plotting software for the 3D images. You can use SolidWorks. I mean, you can get a lot more information on even on the internet who are a pro in this regard.
Thank you, madam.
This is what I have used, so I told you those which I have used.
It's a very nice session and very informative for newly starter. And thank you, ma'am.
Is there any other participants want to ask questions? Okay, ma'am. It's been a very well explained session on the additive manufacturing and the microstructure distribution, the property distribution. It's been a very good source of resource for the business scholars also. We expect such sessions in further, ma'am, in our college. Thank you for your valuable session, ma'am. Thank you.
Thank you very much. Thank you. I really appreciate it. Okay.
Thank you. So there is no another session today. We have only one session today. Tomorrow we have 2 sessions.
Hello, sir.
Sir, tell me, sir.
For tomorrow, any assessment test is there, or there is nothing after validity? It is completed.
Assessment will be conducted at the 6th day only, sir. Saturday.
Okay. Okay.
Okay, sir. Thank you. You can give your feedbacks. The link is available in the chat box. You can give your feedbacks. Thank you, sir. Thank you.
Thank you, ma'am. Thank you so much.
Thank you, ma'am.